Good afternoon, everyone. I would like to welcome all participants to today's webinar hosted by the WaterProof project. My name is Dušica Banduka. I'm from the nova-Institut. We are a science-based consultancy located in Western Germany in Hürth, and we support our clients in their transition to renewable carbon solutions. And today's webinar, as mentioned, is happening within the framework of the WaterProof project. Can you guys see my screen?
Yes, looks good.
Perfect. Okay. Just to give you a short introduction on the WaterProof project, it is an EU-funded research project that started in May of 22, and it will wrap up in May of 26. Our goal is to develop an electrochemical process that converts CO2 emissions captured from consumer waste incineration and wastewater treatment facilities into formic acid. And this developed formic acid will then be tested in 3 different applications. This will be cleaning detergents, like especially toilet detergents, the tanning of leather and fish leather apparel, and also the development of acidic deep eutatic solvents, which will then be used for the recovery of precious metals from waste incineration, ash, and wastewater sludge. Another component of the project is the assessment of social acceptance and sustainability impact of these developed solutions, especially the CO2-based products, and this will take place within an LCA and social LCA. But we will also develop strategies to transfer these technologies to urban communities in developing countries around the world. In this case, it will be Colombia. So here you can see our partners. And in today's webinar, we are excited to welcome 4 different speakers from the field of CCU that will give you a short overview of CO2-derived chemicals and potentials in this field. We are going to welcome Piers Kosinski from nova-Institut, Francesca Di Bartolomeo from Sintef, who is also the coordinator of the PyroCO2 project, Albert Gizasola, and he is from the Autonomous University of Barcelona and also in charge of the Vivaldi project, and Eric Schuler from Avantium, who is also participating in the WaterProof project. And we will also make the slides and recording afterwards available at the WaterProof website. A little bit of housekeeping. So we will first hear the presentations, and then we will later have a Q&A at the very end. So please address the speakers with @speaker, the specific person you are referring to, but also if you would like to state your question verbally, please raise your hand and we can unmute you and you can just speak to them. So with this, I would like to welcome our first speaker. This would be Piers Kosinski. She is a trained biologist and has several years of research experience in optimization of microbial cell factories, enzyme engineering, and enzyme catalyzed polymerization. And after 1-year postdoctoral research in macromolecular and polymer chemistry, she joined the nova-Institut in 2018 in the Technology and Markets department. Here she is a senior expert for bio-based building blocks and polymers, industrial biotechnology, and obviously carbon capture and utilization. Welcome, Pia, and thank you for joining us today. We can see your slides, Pia, but we cannot hear you.
Okay, now. Sorry, I just forgot to unmute myself. So thank you very much, Dušica, and also thank you very much for the nice introduction. And yeah, before we start with the main presentation, or the main part of my presentation on renewable chemicals from CO2 and overview, I will give you first of all a short introduction to the nova-Institut. Nova-Institut was founded in over 30 years ago and currently has a multidisciplinary and international team of nearly 50 scientists that are focused on science-based consultancy on renewable carbon for chemicals and materials. And we have 4 departments in total: a communications department, a sustainability department, as well as an economy and policy department, and a technology and markets department where I'm a part of. And here we are focused, among other topics, on market research, innovation and technology scouting, as well as the setup of customized expert workshops. And we also create and publish a variety of market and trend reports focused on bio-based and CO2-based building blocks and polymers, as well as chemical recycling. And our latest CCU report was published in April 2023 and covers the complete CCU value chain, starting from carbon capture to green hydrogen production, over the utilization part that includes here chemicals, advanced fuels, polymers, proteins, and minerals, all together compiled on 240 pages. And we also included 116 company profiles. And if you would like to have a short insight into the report, you can also download here a freely available short version of the report. Although this report was already published 2 years ago, meanwhile, we have updated the numbers of the CO2-based products included, but we have not yet updated the complete report and published it. So today, I will focus on the CO2 to chemicals part of this report with the updated numbers. In general, if we look into CO2 utilization, there's a large number of projects already implemented and running over the last years that use CO2 as a feedstock for gases, fuels, polymers, single-cell proteins, food and feed ingredients, minerals, and also chemicals. And these different kinds of products can be produced either by chemical conversion of CO2 here on the left-hand side in pink, or via biotechnological conversion here on the right-hand side in green. Chemical conversion, I think, as you all might know, includes the use of conventional chemical reaction systems, catalysts, and energy input to convert CO2 or other carbon-containing gases into various kinds of products. And the most widespread use here also includes the use of hydrogen to reduce carbon and thus make it available for further use. A subgroup of chemical conversion is electrochemical conversion that uses electrical energy to convert CO2 to, for example, formic acid, ethanol, or ethylene. And on the other hand, we have here the biotechnological conversion that includes so-called biocatalyst to convert CO2 or other carbon-containing gases into the mentioned products here at the bottom. And biocatalysts can either be of non-living origin, that means, for example, or refers to isolated enzymes that catalyze the reaction, or also so-called whole cell biocatalysts, so microbial cell factories, living microorganisms can be used to catalyze the reaction and use CO2 as a feedstock. In general, biotechnological conversion, when implemented, engineered, and optimized, have high selectivity, yield, and reproducibility, and we also do not need to add toxic chemicals into this biotechnological reaction systems. In the following minutes, I will focus on 2 chemical conversion processes, hydrogenation and electrochemistry. And when it comes to biotechnological conversion, I will focus on bacterial system, or one bacterial system that is used to produce chemicals from CO2 as a feedstock. So, chemical conversion, the hydrogenation of CO2 to methanol, is the most followed way to produce CO2-based methanol and is used commercially. Currently, methanol can also be produced via electrochemical reduction of CO2, but this technology still has a lower development level as the CO2 to methanol hydrogenation. And this electrochemical conversion to methanol is currently at a TRL of 5. And here we can see the process overview of one of the leading companies in CO2-based methanol production, Carbon Recycling International from Iceland. And here we can see, of course, first we have to capture the carbon dioxide and produce hydrogen via water electrolyzers. Both are compressed first and then put into the hydrogenation reaction to yield then methanol at the end. And in this case here, we need 1.5 tons CO2 to produce 1 ton of methanol. And that reflects a conversion rate of this CO2 to methanol process of 70%. In general, when it comes to the market size and also the market status and evolution of CO2-based methanol, we had a previous evaluation before we published the initial report in 2023. And here we had published a capacity for 2022 of over 100,000 tons of CO2-based methanol worldwide, and a forecast to 2030 with an installed CO₂-based methanol capacity of around 1 million tons. And these assumptions were based on company announcements back in 2022, based on 25 companies that announced to be already active or will be active in the future for CO₂-based methanol production. Methanol is one of the largest volume chemicals worldwide and serves as a building block for numerous other chemicals such as formaldehyde, acetic acid, as well as dimethyl ether. And it can be transformed into fuel via the methanol to gasoline process, or it can also be used to process, to produce polyolefins, so polyethylene or polypropylene at the far end of the value chain via the methanol to olefin process. And since the last 2 years, we have observed a big boost in the investments for CO₂-based methanol, and the current capacity estimated in 2024 is at over 450,000 tons. And if you would like to have a complete overview of all renewable carbon-based methanol that is currently produced or planned to be produced, so methanol coming from biomass, CO₂, and also recycling, I would like to refer you to the Methanol-Institut website, and they have a complete interactive database that covers all the current and future planned implementations of methanol production. Here you can see an overview of the currently active companies in CO₂-based methanol production. We have here Carbon Recycling International that I already mentioned in Iceland, having a 4,000 tons per year capacity in place. Of course, we also have a lot of Chinese companies with large capacities in place with over 100,000 tons. And also in the US, we have a company, Fairway Methanol, that have one of the largest installed capacities currently with about 130,000 tons per year of methanol production. So total capacity in 2024 was over 450,000 tons for CO₂-based methanol production. If we look into the forecast until 2030, as of July 2024, the total capacity forecast of all CO₂-based methanol projects worldwide was at about 13 million tons per year by 2027 and over 60 million tons per year by 2029. And currently, most of these projects are either in the feasibility or pre-feasibility phase or in the engineering phase, but only a certain share of this forecast can be considered as firm, because although we have this ambitious plans for CO₂-based methanol worldwide, a large number of these projects are losing traction as based on the high feedstock costs and an uncertain investment climate. And so a lot of developers are turning away from their initial plans to produce CO₂-based methanol, and this will then also delay the expected beginning of operation of a large number of these plants that are planned for the future. Electrochemical CO₂ conversion, I think most of you already know that. So electric energy is directly used here for the conversion process, and the electrocatalytic reduction of CO₂ involves an electrocatalyst in the electrochemical reduction. And this electrocatalyst can function at the electrode surface or maybe the electrode surface as, itself. And here we have an example of the US-based company Air Company for the production of ethanol, and the conversion rate of CO₂ to ethanol via electrochemical conversion is currently estimated from 20 to 60%. For ethylene, it's a little bit higher. It's estimated from 50 to 80%. So these ranges and the specific conversion rate of the individual process, of course, depends on the specific setup of the electrochemical conversion and, of course, on the electrocatalyst that is used in this process. And here we have an overview of companies and startups active in electrochemical CO₂ conversion to a large variety of chemicals. So we have the already mentioned US-based company Air Company. They already have successfully produced ethanol via electrochemical conversion, and they upgraded this ethanol and sold it as vodka, so alcohol, and they also produced a fragrance based on this CO2-based ethanol. Also, we have the Brazilian-based company Braskem, one of the largest or the largest bio-based ethylene and polyethylene producer currently, and they are also now engaging in the use of CO2 to produce ethanol and ethylene. And also, we have European-based companies here, for example, Dioxycle, also engaged in the production of ethylene in France. And we have the Belgium-based company Decarbon that is electrochemically reducing CO2 to carbon monoxide. Now, biotechnological conversion, I think the most of you are familiar with the company LanzaTech, which is one of the leading companies in biotechnological CO2 or carbon-containing off-gas conversion into chemicals. LanzaTech is using an acetogenic bacterial system that converts waste off-gases with a large amount of carbon monoxide to ethanol. They are also currently engaged in other chemicals, as for example, isopropanol. And the ethanol is already produced on a commercial scale via this acetogenic bacterial system, and the ethanol was already successfully upgraded into jet fuel that was used a few years back in a commercial flight of Virgin Atlantic. And LanzaTech is also, for example, collaborating with L'Oreal to use the ethanol to then produce polyethylene that is used in the cosmetic, in the packaging of a cosmetic bottle for L'Oreal. And also here we have an overview of different other companies that are biotechnologically converting CO2 in different kind of chemicals. For example, we have the German-based company BFAB, and they are using a hybrid approach. They combine electrochemistry with biotechnology. So they first electrochemically produce formic acid that is then used as a feedstock for biotechnological conversion to produce, for example, succinic acid. Then we have the US-based company Chemvita. They are producing ethylene biotechnologically. And as I already mentioned, the US-based company LanzaTech, they currently have a worldwide capacity of ethanol of 200,000 tons. And it is expected that they will increase their capacity until 2030 to about 700,000 tons for CO2-based ethanol production. And last but not least, we have the one of the leading companies in the production of lactic acid and polylactic acid, NatureWorks. They collaborate with the biotech company Callista to produce lactic acid from CO2 via biotechnological conversion. So, and if we all take this together and also combine it with the other renewable carbon sources, so biomass and recycling, we have developed a scenario on how the chemical and derived materials industry may look like in 2050 if we follow the goal and transition this chemical industry from the use of fossil carbon to the use of renewable carbon completely. In 2020, we can see that, of course, the highest share was still fossil-based carbon here with 88%. We also had the share of bio-based carbon used here of 8%, CO2 only 0.03%, and recycling 4%. And we expect a compound annual growth rate of the chemical and material industry of about 2.5% until 2050. And here on the right-hand side, you can see the shares that we assume or put into this scenario on how the renewable carbon sources will be distributed in 2050. So 20% will come from biomass, 25% from CO2, 50% from recycling, where the virgin feedstock is bio-based, CO2-based, or recyclate, and 5% were coming from recycling, mainly mechanical recycling from virgin-based, from fossil-based virgin feedstocks here. And yeah, with this, I'm at the end of my presentation, but first I would like to highlight our next upcoming biggest conference that we have on renewable materials. So our Renewable Materials Conference in September. And here we have 3 days that are completely focused on the use of renewable carbon. And we have topics as as more overarching and strategy and innovation topics as the defossilization of the chemical industry. We also have a 1 day completely dedicated to fossil-free plastics, and here we include monomers, polymers, and plastics coming from from biomass, CO2, and chemical recycling. And also we have a session on biodegradation on the 3rd day. So if you're interested here, we still have a discount code available until the mid of August. And if you would like to have more information or need more information, you can also reach out to my colleague Anke, who's also here in the webinar. She is one of the main program managers of this conference. And yeah, with this, I would like to thank you for your attention, and I'm happy to take your questions at the very end of this webinar.
So thank you very much, Pia. First of all, thanks for promoting our conference. And yes, please reach out to me. I will write my email address in the chat in a moment. Sorry for the sound here where I am. My meeting room is very, very sound intense. So it's not your computers, it's me. But without further ado, I would like to present our next speaker, which is Francesca Di Bartolomeo. She is a senior scientist at SINTEF, specializing in industrial biotechnology and microbial cell biology. She holds a PhD in yeast cell biology from TU Graz and a postdoc in systems and synthetic biology at Chalmers University in Sweden. As a project manager in the Center for Research-Based Innovation on Industrial Biotechnology, Francesca leads initiatives like the EU project PyroCO₂ and the collaborative project CO₂ Value, focusing on CO₂ conversion into sustainable products. So Francesca, great to have you here. The stage is yours.
Thank you so much. I can imagine that you can already see my screen. If you can confirm that, then I can start.
I can do that.
Perfect. So thanks a lot for having me here today in this webinar. It's exciting to meet colleagues from other projects within the same framework. So thanks a lot. Very happy to participate. So today I will give you a bit of an overview to highlight some of the key activities that we are doing at SINTEF within the field of CCU. So my presentation is titled Pioneering Sustainable CO₂ Conversions to C3 Chemicals. So we have this focus on the C3 chemicals production, but also lipids production for food and feed application. As you can see from the title, we have already 2 distinct applications which are very different to each other, but share the commonalities of having CO₂ as a starting point for making these different materials and all the technological implication of that. So today I will give you just a short introduction about SINTEF, who we are, what we do. Then I will move to the part 1 of this talk, which is focusing on the PyroCO₂ project and the C3 chemical production. And then I will close with the latest developments on the feed ingredients production using CO₂ as a feedstock. So about us at SINTEF. For some of you, or the many of you that don't know about SINTEF, we are one of the biggest research organization in Europe. We are independent. We are no profit. We are over 2,200 employees by now, different nationalities, and we work with a very wide range of industries, but we're also developing, joining, and coordinating EU proposals and also national initiatives. As a no-profit research organization, this means that whatever research we do, whatever profit we do, is reinvested into the activities within SINTEF itself. So our vision is a technology for a better society. And as a large research organization, we are focusing in different areas which are aimed to make us competitive, technologically competitive, but also we have a great focus on the societal benefits. For instance, we work on sustainability. This is a big word that involves a lot of different topics, and we are trying to make progresses there. So since we want to make progresses in so many of these fields, it's important for us that we have labs, infrastructure, always updated to address all the most important questions for society, but also for industries. This is just some screenshot of some of our labs. And as you can see, we have a really vast variety of application and expertise. And when it comes to me, I'm here in the corner doing biotechnology, but I'm very much collaborating with a lot of my colleagues at SINTEF, for instance, the people at the CO₂ laboratory at Tiller. So as I said, I am representing today the Department of Biotechnology and Nanomedicine and our expertise in everything to do with bioprocess development, to be very generic and quick. We are also collaborating very much with the Process Technology Department. And the people at the Process Technology Department at SINTEF, they are very much interested in the very core industrial application of some of the development that we do at biotech. And we also collaborate very much when it comes to joining forces between the capturing, the refining of the CO₂, in this case, and the biotechnological utilization of the purified and refined CO₂. And also the collaboration, it's very important since, as you will see, we do also large-scale experiment. Therefore, we need to look beyond our biotech laboratories and more at the industrial application of what we are developing. And speaking of laboratories, I specialize in industrial biotech, and we have more than 30 years of experience in microbial development, cell-based production, advanced research analytics as well in these fields. And now within the field of CCU, we are also teaming up with the Tiller CO₂ capture pilot plant that gives us the possibility to bridge, as I said before, within SINTEF, capturing and refining with utilization of the CO₂ to make different materials. But let's move on to the actual project and the science behind all of these talks about SINTEF. So converting CO₂ emission into products, this is one of the ambitions of a number of projects that we have at SINTEF. We really want to put CO₂ into good use. And as a biotechnologist in the core, our focus is to use fermentation to have this utilization and this transition from CO₂ into products. In this presentation, you will see, as I already mentioned, that I will talk about two main products, C3 chemicals and specifically acetone and feed ingredients. And this also gives you an idea of the flexibility that we can have in value chain of this kind. The value chain that we are considering are always starting from CO₂ from various sources, which could be, for instance, industrial CO₂. There needs to be further refined, which we also do. Then, of course, the link between capturing utilization, it is something that is currently really on focus, and there is a lot of work that we are doing at Tiller specifically to try to bridge this utilization, this capturing and refining with utilization part. Then, of course, we need hydrogen as an energy carrier, as an energy source for our processes, which are then resulting into a fermentation that takes CO₂ as carbon source. And then we have the microbial conversion in a second fermentation then to produce chemicals, but also, as I said, proteins, oils, and other feed ingredients or other platform chemicals. One thing that we are also working on, and I will show it more in the next slides, is how to further recycle the CO₂ that generates usually from the second fermentation step. This being an aerobic fermentation generates some extra CO2 or generates some CO2 that we will need to capture it back in order to conserve as much of the CO2 and transform it into products. So this is the kind of value chain that we are considering in the vast majority of our projects, looking into different aspects of this what I present here in these slides. But let's get started on the PyroCO₂ project, and some of this work is also done at the SFI Center for Industrial Biotechnology that we lead at SINTEF. Is a Norwegian 8-year center that really focuses on industrial biotechnology, as the name says. So the PyroCO₂ project is a green. It has been developed under the Green Deal calls. The first one, it was awarded fundings in 2021, late 2021. And as a project, I would call it a demonstrator, a scale-up project, because what the core of this project is really to bring the technology from TRL 4, as we started in 2021, to TRL 7. And which technology are we scaling up? We are scaling up the technology that allow us to go from CO2 to acetone via a value chain like I showed you just before. Then from acetone, this is a 3C chemical, as I was saying, gives us a possibility of further diversify and having more value out of this, which could be in the form of chemicals, in the form of materials, or in e-fuel. So when I speak about TRL7, this is a demonstrator fermenter, and this applies primarily to the acetone production, which is very important these days. But why acetone? The 3 carbon molecules are not very easy to access biologically. Of course, acetone is a marketable product these days that comes as a byproduct of the cumene process for the production of phenol. So there is this cumene process that gives us phenol, and acetone is a byproduct of this. So it's really as unsustainable as we imagine it to be, fossil-based, and we are really not only want to transition out of the fossil-based chemicals, we also want to enter the so-called 3 carbon molecule space, and this is why acetone is very important for us. As you can see in these slides, there are many other chemicals, like we heard also before, like ethanol, ethylene, acetic acid, that are currently produced in CCU project or by companies that are operating CCU technologies. And they are very, very important. They are platform chemicals that really give us the possibility to make way more. But really accessing different spaces, different chemical spaces, and also developing more ingredients and starting point for making more and more products, it's very important. And also it gives us a possibility to access a lot of different products at the end, for instance, pharmaceutical, cosmetics, plastics, and brings the CCU technology really to a next level. So this is what we are trying to do. But even though I'm a biotechnologist, and I'm obviously very much biased into what I know best to do, what we are doing is also combining biology with chemistry. So we want to use the flexibility of biology, the possibility to use strains, to adapt microbial strains, to genetically engineer them as well. And this is a very good process, and very sustainable as well, even though there are a lot of bottlenecks when it comes to production, to purification, and so on and so forth. But in any case, what we do is combine biology with chemistry. And with chemistry, it's basically everything that has to do with the chemocatalytic use, with the chemocatalytic diversification of, for instance, acetone to chemical materials and e-fuel and so on, so that we can produce all of these different products at the end. But as I was saying before, the core message and the core work of the CO₂ project is scale up and demonstrate, which is not really as trivial as as it might sound. So many of you might know that. So when we started the project, we started with a technology that we know it would work, and we know it worked at the lab scale. So let's call TRL4. Then throughout the years, we've been working towards scaling up the fermentation to around 150 liters. Now we are currently working on the 1000 liter. And as we speak, and how we scale up further, we are also developing and building the final demonstrator plan. So part of the project is also everything that has to do with the building, putting together this demonstrator. So it's a quite large project in that sense. But progressing in the TRL scale is not an arrow that goes into one direction, as we see here. The development is iterative. So we are keep going back and forth with the arrow going to TRL4 and 7. So meaning that there is always a lot of optimization that is still happening at TRL4, and this is the norm in this kind of projects. You need to always optimize. You need to always go back to a smaller fermenter to try to understand better how to optimize and further scale up. So when we started here, as I was saying, we focused a lot on the production of acetone, setting up fermentation, improve the strain, and so on. Then we started building up and also testing the 150 liter and a 1 cubic meter gas bioreactor at our colleague at Norse, still in Norway, in Reykjavik. And here what we did, we used the data that we generated in these reactors to further test the strains that we have improved and engineered, to also gather data for both the CFD and the kinetic modeling, and also try to understand how we can optimally recover the acetone and things like that. So, and then obviously process integration and optimization between the two the two fermenters. Here is just some pictures of when we were starting to look at things and work in a team to try to make it function in a very integrated way. Yes, as I was saying before, it is very important to look at the different scales, but also to look forward and to look backward at how we can optimize the process further. And why it is so important to have an intermediate scale at the first place. We call it mini demo. It is important because there is always a multiple steps, and then there is the integration of the two fermentation steps that you cannot just improvise at a larger scale. Of course, the smaller TRL4, it does not give you really satisfactory answer about the demonstrator will work, and therefore we need to test things at an intermediate scale. Then, of course, we need to identify the challenges with scaling up that you can also start to see and identify going from TRL4 to 5 or 4 to 6. Then, of course, for the further chemical diversification, we needed some material to let them work and test the acetone that we produce biologically. And then, of course, building experience and knowing everything that we need to know and learn that it will be used then when we are in the position of operating the demonstrator scale. Yes, and here's finally the CO₂ demonstrator that is currently being built in a location which is not very far from where I'm sitting at SINTEF. Here's just some prospects of the building that we are putting up that will accommodate our large fermentation system plus collaterals. Basically everything also that has to do with the recovery of the products, making the media, everything from A to Z. Yes, here is where we are. I haven't mentioned it, but we are based in Trondheim, which is in the middle of Norway, really. As you can see, this is the SINTEF headquarters where we are based, where I have the labs. And here, maybe 5 minutes by car, 9 minutes, 10 minutes by bike is the lab where we will have the demonstrator at Tiller. And another very important things of the Tiller site, as I mentioned before, is that we have the multi-phase flow laboratory that also is the host of the Tiller CO2 capture and pilot plant that will also give us the possibility of having this direct bridge between a pilot facility, a pilot research and test facility that operates carbon capture and refinement, and the Pyro CO2 demonstrator that is all about transforming the CO2 into something else using biotechnology, also using chemistry later on. Yes, so this is the end of the first part of my presentation that is about Pyro CO2 primarily, and is about the C3 chemicals and all the demonstration effort of a process like this. Then we move, as I said, from C3 chemicals, from acetone to feed, and specifically feed ingredients like proteins and lipids, still from CO2. But in this case, of course, when we say from CO2, we also imply that there is hydrogen, that there is nitrogen sources, and so on and so forth, CO2 as a carbon source. And this, the data that I'm going to show you now, this is coming from other in projects that we are running at SINTEF. But in any case, why feed? Why we want to give feed a focus? Well, feed is definitely a focus for Norwegian researchers like us at SINTEF. There is a massive need for sustainable feed sources and feed ingredients for Norway. The salmon farming, but also the fish farming, it's a big source of revenue for the country, is a big source of export, and this is going to grow, is projected to grow, of course, and it's also a product that dramatically needs to be more sustainable than it is now. The feed ingredients that are sourced to this day are primarily Brazilian soy. Nothing wrong with that, but this has a number of environmental concerns. And most of all, I mean, it's very important to also make the industrial CO2 that is anyway generated locally into good use. And feed ingredients is something that it's very in high demand these days. So this is why we got quite some focus on that, and we addressed it by starting to look into what we could do. We started with omega-3 fatty acids. This is a product that we currently generate, and as you can see here, following the value chain that I showed you before, we go from CO2 to growing these very nice non-GMO strains that are very good at accumulating lipids. They accumulate up to 80% lipids of the entire biomass. And most importantly, 30% of these lipids is omega-3 fatty acid. Omega-3 fatty acid is a very important product that can have a high value application both in feed and also in food. We are not there yet. So far, we are just making all the technological development to make sure that we can produce a lot, that we can produce efficiently, and also that we can effectively extract these oils also in a sustainable fashion. That is not obvious, especially when you do some techno-economic analysis to see where are the, let's say, the money sinks of the process. So we are working on that. But as I said before, it's also about how we use CO2 efficiently in our process. So in the project that we are running for the production of the lipids, we are also starting integrated membrane system that gives us the opportunity to enrich the CO2 that is just generated from the second fermentation step. So this is a work that was initiated at SINTEF already some years ago. We have some nice paper on this selective CO2 membrane system and also several patents on the topic. What hasn't been done yet, and we are doing it now, is to try to see how it works connected to a fermentation system. And this is also part of the developments that we are running at SINTEF. And this is a little, it's a picture of our small scale setup where you have a reactor vessel. Here is just a mock fermentation. Of course, our media is not transparent at all, but as you can see here, this is directly connected with a membrane cell that has the capacity of let's say, enriching and filtering out the oxygen versus the CO2, so that in the second phase of the development, we can then circulate this enriched CO2 back into the first step. This is very much under development. Hopefully we will publish this study soon, and we will continue also using high pressure fermentation system to test even more how we can collect and utilize and recycle, so to speak, the CO2 that derives from the second fermentation step. Yes, then along these lines, I would also like to introduce a very recent project that got awarded and we started on April 1st. This is called CO2 value, and we want to, again, convert industrial biogas streams into fish feed, and in this case it's not only oils but it's also proteins. And one of the things that I would like to highlight about this project is really how much we look into the different steps of the value chain. We are not just looking at how much acetate, how much proteins, how much oils we make, but we also think about where the CO2 is coming from, how it is processed, and for this we are collaborating with the Ocean Loop, which is a company that it's very much involved into sustainable refining of the CO2. Then at SINTEF, also together with again on the gas fermentation, and NOMI, that is a feed producer, also a Norwegian company, and Technical University also here in Trondheim, we are addressing everything that has to do with the fermentation setup and how we can accommodate the quality and the kind of CO2 that comes from the capturing facility. Then we have the recycling part involved, and then here we are also working with Skrettings, which is a very large feed company that serves pretty much the whole world. We are trying to understand which kind of formulation we can develop starting from these materials. So it's a quite ambitious project because it involves all the different steps. And we are very excited to have started with this this year. And also it's very important to mention that it will give us the possibility to gather even more data for doing all the LCA and all the TA, which is the techno-economic assessment, which is super, super important in project of this kind. And with this, I conclude my presentation. You can take a look at who we are and what we do. You can reach out, you can ask a question. I will be here until the end of the webinar. And with this, I thank you very much again for having me.
Thank you very much, Francesca. So I would like to encourage everyone once more to state your questions in the Q&A section and also address the specific speaker you're referring to. And I would also like to welcome our next speaker, who is Albert Gizasola. He is a full-time professor at the Chemical, Biological and Environmental Engineering Department at the University Autónoma de Barcelona, and he has devoted his last years of research in resource recovery from waste. Particularly, he is leading the Horizon 2020 Vivaldi project, which is aiming to transform CO2 to value-added organics through the use of novel biotechnological approaches. Thank you so much for joining us today.
Thank you. Hope you can see my image.
Looks perfect. Thank you.
Oh, thank you. First of all, thanks for having me. It has been a very interesting webinar so far, so I hope I can keep up the level of the other presenters. So my name is Albert Isasola. I'm a full professor at the University Autónoma de Barcelona, and I will explain the project at Vivaldi, which is going to finish in this month. So it's 4 years of research. First of all, this project is based on the novel CO2-based industry. I don't need to explain this because it has been told before, but the idea is to start a new era, to pioneer a new era of CO2-based chemicals. What we want to do is we want to transform the linear structure of companies. We want to transform it in a circular concept. This project started, as I said before, 4 years ago, and it will finish this month. So it's a project with 16 partners. It's a typical H2020 project with a €7 million budget. And we have different partners, which are bio-based industries, which are technology developers and users and knowledge hubs. As you can understand, I cannot summarize all the project results in 20 minutes. So you will see at the right hub, at the right up corner, the partner who is engaged in that. And if you have any questions, I will try to solve it. Today, I will only showcase the most exciting technical results that we have obtained. It is the structure of our partnership, bio-based industries. We have 4 different bio-based industries, which have technology developers and users of the organic acids that I will comment, and some transversal partners. The objective of Vivaldi is to use CO2 emissions from bio-based industries, in this case, pulp and paper, food and beverage, biofuels, and biochemicals. And we want to convert it to a building block. So it's similar to what Francisca has explained. So we are going to do a conversion of CO2 to formic acid and methanol, and they will be the building block for a microbiological process. The bio-based industries do not only produce CO2 emissions, but they only produce wastewaters, which contains a lot of nutrients, ammonium, and other cations that can be also used for the fermentation process. So we have engineered a novel fermentation process based on a yeast. In the past, it was called Pique Pastoris. Now it's called Comagatella fafi. And this is a yeast that can transform formic acid and methanol to 4 different organic acids with different market penetration shares. We have a very common, let's say, lactic acid. Then we have itaconic and succinic acid, which are present acids, and then we have 3-hydroxypropionic acid, which is one of the 10 platform acids for the future. So the idea is to transform CO2 from real industries to acids that can be used inside of the same project, so we can start again, or we can sell them. So this is what we call the CO2-based industry. Okay, I will explain a bit the major results obtained in each of the cases. For the first part, which is the purification and conversion, we decided to go for MDA-based absorption. Okay, the absorption has a lot of advantages, but maybe the potential drawback that you can find from a theoretical point of view is a slow CO2 absorption rate. How did we solve that? So we add an enzyme, we add carbonic anhydrase, okay, and we use the absorption based with this enzyme. So I'm not going to go into all the details, but what we achieved is a much better and much more efficient process than the conventional absorption process with MDA only. The conditions were milder, we used less energy, and the costs were reduced up to 25% with very high CO2 capture efficiency. We achieved that not only in the lab, but we also use a real industry from Sweden, some pine, and we capture CO2. As you can see, it's not CO2 coming from fermentation, so it's not 98% of CO2. It's a CO2 that only contains 30% of CO2, so that was a big challenge as well. What do we do with this CO2? Once we capture and purify it, we do CO2 electroreduction. There are a lot of techniques to convert CO2 into building blocks. We use electroreduction because, as I said before, we want it to be compatible with biological process. It's it does not require a lot of energy and can be easily mixed with a power to X concept. Why are we producing formic acid and methanol? Because they are very building blocks. They are building blocks that contain a lot of energy, and they can be used as a carbon sources for biotechnological processes. These 4 years, we also realized that formic acid has also a very good market share as a standalone product as well. Okay, so the objective is to convert CO2 to formic acid and methanol via CO2 electroreduction. We started from lab. We started with GD electrodes, and we were not only focusing on having a lot of electrons going to CO2, but also we were focusing on having a lot of carbon going to formic acid. Sorry, I said CO2, formic acid. So our objective is to do a very good mass and electron balance, so that all the electrons were converted into formic acid. And we built a very small setup like this, and we had very good results. The maximum thermodynamic level for carbon conversion efficiency is 50%. The maximum thermodynamic level for all the electrons going to formic acid is 100%. And as you can see here, I'm just going to go very sharp on the results. Our results were very good at very small scale. We decided to scale this up. We went to 10 square centimeters, to 100 square centimeters, to 300 square centimeters at lab scale, and the results were also very good with team-based GD. Okay, we did not only stop at its lab scale. We went to pilot scale in facilities in Belgium. You have the conditions here, but I know that you have no time to read them all. But the idea is that we went one step beyond in our aim to scale this up. We obtained very good results with more than 1,000-hour test. This is very important for me to highlight. Those who have seen electrochemical processes, probably the x-axis, it's minutes or hours. So we really studied long-term and long scale. So this is something that we are very proud of. And as you can see, the Faraday efficiency was very high. The formic acid production was also very high. And we also tried a different compound, which is a bismuth, and also with very good results. Also at long term and high scale. Finally, we have another partner that used this format that we were producing, and really we had this formic acid at different percentage of weight that could be used for fermentation. So my first idea, we could easily go from CO2 to formic acid, and with an efficient way from CO2 at 13% to concentrated formic acid or to potassium formate. This is going to be used in fermentation, but also we need some nutrients. Particularly, we need a lot of ammonia for the fermentation processes. So we did this fermentation. So how did we recover these nutrients? We use bioelectrochemical systems. These are a very emerging technology, and I will just go through it a bit fast. So the idea is that we have bioelectrochemical systems. For those who don't know that, we have some biomass in the anode, which is able to interact with the anode, and it's able to share electrons. So what we do, we degrade organic matter, and the electrons flow from the anode to the cathode once a small potential is applied. This flow of electrons from the anode to the cathode creates an imbalance, a charge imbalance, and then if you use a cation exchange membrane, the most, let's say, the most active cation, or the cation with higher concentration, goes from the anode to the cathode. In this case, we wanted ammonium, so we wanted an anode with a lot of ammonium concentration, so the ammonium goes from the anode to the cathode. Since we are producing hydrogen in the cathode, what happens is the pH increases, so we have an alkaline environment, so ammonium is transformed to ammonia gas. And then we add a hydrophobic membrane that only permits the transfer of ammonia to a recovery chamber, and we apply some acidic conditions. So we transform it as ammonium sulfate. So as you can see, there is no transformation of ammonium, There is no oxidation of to nitrite to nitrate. There is no reduction to nitrogen gas. So it's a classical recovery process. But we use bioelectrochemistry to have very efficient and low energy conditions. If you want, I can explain a bit more about that. But okay, these are the cells that we use. It's a 1 liter cells. We had many of them. And we had a lot of results under very different conditions. That was 2 years of investigation and optimizing. I'm not going to comment them. I'm just going to show you the best results. We use different values of sulfate to recover ammonium. And as you can see, we could deliver, let's say, the ammonium sulfate with a very high concentration. This I didn't mention, but inlet was from 4 to 8 grams of N per liter. So for those who have worked with this, that's very difficult to be obtained because of inhibition. And our effluent was also 4 to 8 grams per liter, of course, because it was 100% recovery. We use not only sulfate, we use phosphate, we use nitrate. So we had different amounts. And as you can see, the pH tends to be very acidic or very alkaline. So this is something that we really didn't want. So we were able to decide an effluent with desired concentration, but very acidic and very alkaline. We applied control strategies, or pH control strategies, engineering strategies, and these are the first results that I want to show. And I want to highlight something that maybe, so the good thing about this process is that we recovered 100% of ammonium, but with a very low energy. So as you can see on your left-hand side, less than 1.5 kilowatt-hour per kilogram of N recovered. If you compare this to the values of ammonium production, Haber-Bosch, or if you compare this to the values of ammonium removal, nitrification, denitrification, it's less than 1 order of magnitude. So we are dealing with the ammonium issue, let's say, no? The very energy intensive ammonium production and removal with this level. And the rates are also quite good. So we obtained rates up to 200, less than 200 grams of N per square meter per day, which, if you know about the bioelectrochemical systems, is the higher rates obtained so far. We also try to use only a two-chamber system and use a conventional membrane contactor, which is something that maybe one can be thinking at first, not to get that complex with a GDE. And we tried that also compare the two-chamber system with a three-chamber system. Again, I'm going to be very fast. We did a lot of effort on optimizing the cathode. That it's very important to produce a lot of hydrogen to create the imbalance. I'm not going to go to all the details, but you have to believe that we created a very good cathode for hydrogen production. And also the results were very good. A bit less efficient than the three-chamber system, but I have to say that more easy to work with. So very high recovery rates compared to conventional bioelectrochemical systems, very low energy utilization, and a lot of efficiency. And if you want, hydrogen as a subproduct. Okay. Then we have formic acid, we have methanol, and we have this Comagatella-Fafi fermentation process. Okay. What can we produce? These are the four acids that we want to produce. Each of the acid gave us different problems. So we started, and I have to say that we genetically modify different strains to produce each acid. So each acid was studied in parallel. You cannot put it together. So I'm going to comment to have one slide for each acid, but every of these slides is almost 2 years of work because it's very difficult to go because it's not in the, let's say it's not in the literature. We had to develop the strains, and we have to engineer the operational strategies. For example, in the case of lactic acid, the main issue was that once the lactic acid was produced, it was directly consumed. That is the first problem that you can find with these systems. That lactic acid is very nice, it's very produced, but of course it's a very good substrate for them. So we had to do a lot of genetic engineering to avoid that. And I'm not going to go to the details, but I want you to see the titers. I think this is the most interesting thing that we had obtained. So from methanol, we obtained a very good titers of nearly 20 grams per liter of lactic acid. If you want more details, I can give it to you. The case of itaconic acid was also very complex, so we have to insert the pathway for itaconic production in the yeast that was from scratch. And I have to admit that we obtained very good results in the first month, so with the first trial, so we could have some time to improve. And the things that we did is try to work at different pH. And why did we choose lower pH? Because they are very easy to downstream in the future. So we could have yeast production and a very low pH and a very high titers, up to 80 grams per liter with very high yields. Succinic acid was very difficult. There are two ways of producing succinic acid involving the TSA. You can go the oxidative TSA pathway or the reductive TSA pathway. In both of them, we find some issues that, for example, there was a lot of malate production in one case, and in the other case that the biomass is not growing. I'm not going to show you a lot of results on this, and this is, I have to say, a good symptom for me, because that means that the results are IP protected, and we obtained very good results. So you have to have some faith here and believe that we obtained very good results, and hopefully you will see in the future. But in theory, the start was very difficult, and we obtained very high titers, up to 100 grams per liter. And finally, 3-hydroxypropionic acid, which is a platform acid for the future. We also did a lot of genetic engineering here, and we obtained very good results, very good titers. We use with bioreactor, we work with flask, and the results were very good. Following the concept that Francesca was mentioning, we also wanted to integrate the electrochemistry with fermentation. So we achieved very good results, let's say, in a three-step production. So first we produce CO2, then we recover ammonium, and then we have this fermentation. But we were thinking if we could do it in one pot or in a single phase. And as we also obtained very good results in this field, that I cannot disclose that much, but we could directly produce 3-HP, hydroxypropionic acid, from CO2, integrating the three steps together. So using the formic acid that was captured in the first step, using the ammonium captured in the second step. And I cannot explain these results, of course, there is a lot of detail, but let's for you to, the green one is the one obtained with all of our products, so coming from CO2 and from wastewater, and the other three of them are obtained with commercial. And as you can see, they have similar profiles. That's the only thing that I can explain, let's say. So downstream processing, we also, despite our project was a reaction, we had a partner on downstream processing, which is a very important partner. Procession, and what they did, in short, they do a characterization on the broth composition, because we wanted to produce acids from the broth, and they did a lot of theoretical study, and then did the process flushing for each acid. I'm not going to go into detail, but we had studied that. I will skip this because on time. And this is a very important concept that I want to give. This is the last big concept that I'm giving to you, is that we realize that a medium that is very good for electrochemistry, maybe not very good for fermentation, and may not be very good for downstream. Downstream people want very simple medium, electrochemists want a very, very simple medium, and fermentation people want a medium with a lot of different things. And if you want to do a one-pot, let's say, process, you have to think about that. Finally, last two slides. We did use our products in the industry. Novamont did a very, very nice plastics about it. We did some cutlery. We did some plastics with very good mechanical properties from the succinic and from the itaconic. So we went from CO2 to real materials. And with nutrition science, they tested our biolactic acid against the conventional acid for the production of food for animals. So, and we had very good results, so it was comparable. I'm not going to comment, but we did LCA, we did social LCA, we did market exploitation as all the partners, but today I will only explain the technical, so please excuse that I don't talk about the work of Peter and Isle. I want, you know, being a coordinator is such a good effort, and I want to say that I had the best consortium ever. I'm sorry about the other coordinators. And thank you very much. Sorry if I take couple of minutes more, but
so thank you, Albert. We will right away go on with the next talk. So our next speaker is Erik Schuler. Erik is a process engineer with 9 years of experience in CO2 conversion. He holds an MSc in chemistry and physics, specializing in CO2 plasma chemistry, and a PhD focused on sustainable polymer production. And polymer production from CO2, and both the master and the PhD he became from the University of Amsterdam. At Avantium, he now develops routes for CO2-based polymer production, specializing in process design, optimization, and integration. And he is passionate about linking fundamental science with process design to enhance industrial relevance. So, Erik, great having you. Please share your screen, and looking forward to your presentation. And we can see your slides, but you're still muted. Erik, you have to click the icon with the microphone on the...
Does it work now?
Yeah, wonderful. Thank you.
And you can see the slides properly?
Looks great.
Yes, we can. Thank you.
Okay. I can't really see much here, so I'll just have to trust it, I guess. Thank you very much. I'll try to be a bit brief. And yeah, I'm from Avantium. Thanks for the nice introduction. And I want to give you a bit of an idea of what we try to make from CO2 and why. So we're also part of the WaterProof consortium. I work in the Volta department, where we mainly do electrochemistry. We go all the way to polymers, but Avantium is a bigger company than that. Most people might know it from Relief or PEF or ICSI. That's all sort of the same, where we make PEF as a bio-based alternative to PET. And at Volta, we basically go the next step. We don't use bio-based things. We use CO2, convert that into chemicals. But also, as we have such a polymer background within the company, we try to make polymers from CO2 as one of the things. We're listed at the Euronext in Amsterdam, are headquartered in Amsterdam, and it's probably 150 patent families. About 300 employees are at Avantium. Yeah, why do we use CO2? Well, if we don't want to use fossil, there's 3 other ways of carbon. Carbon is in most things. There is plant-based, where we make also polymers from. There's man-made, so you can recycle carbon, or there's air-based. So air-based CO2 is one of the 3 main carbon sources if it's not fossil carbon. So that's why you should use CO2 as an air-based carbon source if you want to not use fossil ones anymore. I'll quickly go over that. At Volta, it's quite an older group already, founded in 2012. It was from Princeton in the US, and we moved over in 2016 to Amsterdam when the founded company Liquid Light was acquired by Avantium. And now in 2025, we keep growing and we keep building this electrochemical CO2 conversion portfolio. Why do we want to use CO2, and why do we want to use electrons to do that? Basically, we can valorize fossil and CO2 and reduce fossil carbon demand. It's actually a quite abundant carbon source. very diluted in air, but there's many point sources, for example, and it needs to be removed from the atmosphere to challenge the climate crisis. There is a potential to couple that also with renewable electricity. So you could, for example, reduce intermittency, use peak power there. So you can use green carbon and green electricity. And there's a broad product range for that. And ideal, I just showed a few things here you can make from it. We focus on formate and oxalate. We think they're ideal targets for this sort of process because you keep a lot of the mass from the CO2. So you make a lot of product out of 1 ton of CO2, if you will, and you don't have to put so many electrons in. Electrons is the expensive part. So making something without any carbon, reducing it all the way, is a pretty inefficient, especially economical way of making products. Maybe you should make your ethylene or ethanol from something else than CO2, at least for now. What are the main pathways we use at Avantium? Basically, we make formic acid. We start with CO2. Everything starts with CO2 to formate. My colleague Brian gave a talk in the last webinar. I think it's recorded if you want to have all the details on that. I have a few small slides, but he went into depth with that. So no crazy technical details today, unfortunately. I'll give more of an overview of the routes and why we want to make what we make. So we make always turn carbon dioxide into formate, and then in the waterproof process, we make formic acid from that. So we basically acidify it. Also electrochemically, you have formic acid. Or the other direction is going via a few steps in between, making a C2 carbon molecule by formate to oxalate coupling. And then you can go all the way to different products like glycolic acid, oxalic acid, and eventually make polymers out of it, which we do, for example, in the Hiccups project. What do we do at Volta? We work on different scales. We work from TRL, let's say 3, all the way. We want to go to 9, of course. And you can see a few of our demonstrators here. So we have smaller lab scale on the bottom left. We have automized setups where we can test in quicker succession at smaller scale. And then we have the container units that keep growing and have been, for example, on the right, you see it at a power plant of RWE in Germany. So they're put in place at a relevant site, and we test with different CO2 sources. So we had power plants, cement plants, we had a Climeworks unit. So we're not capturing the CO2, but we try to use as many different sources as possible. And try to increase the throughput. So we started with the Ocean project, which wrapped up in 2023, where we had a single cell with 250 grams of formate per hour and 5,000 hours of stability. Now we have WaterProof that's being developed. We want to increase that quite a bit. We have then a cell stack where we go to 1 square meter of cell, 1.5 kilograms per hour formate. And we increase and do salt recovery and product separation. So you integrate more also. And then the next project that just started is then Iconic, that builds on the WaterProof process. There's going to be a bigger cell stack even, and then we're going to go to 50 tons per year formate. And we fully integrate upstream and downstream. So that's a bit the development process of the CO2 to formate. And then comes the how do you go to your actual products after that. So this is our main core technology at this stage. What are the critical numbers? Basically, what we have to really increase is the conversion efficiency to make better use of the expensive electrons. We have to get the lifetime up, and we have to improve the scalability of this process. So it's a lot about upscaling and increasing the efficiency at this stage. Formic acid, what is formic acid used for? That's what we make in the WaterProof process. In the WaterProof process, you can see basically we work with a wastewater treatment and waste treatment partners. That's where our CO2 comes from there. Basically from biogas, for example, we do the electrochemistry, we make formic acid. And then we make consumer cleaning goods, tanned leather, and deep eutectic solvents, which we can in turn again use in the waste companies, because these are used to get metals that are in the waste. So all the metals you put into your bin have to be extracted, so you can use deep eutectic solvents, and those you can make from the CO2 by burning the waste or by fermenting the biogas. So we basically this is in view of time, I'll go quickly over that. This is the process here. Again, our core technology, we put a CO2, which we turn into formate in step 1. On the other side, you always need to couple your reactions. We basically make hydrogen peroxide, and in the electrodialysis unit, we make the actual formic acid. And then in the step 4, you basically recover that. So there's a nice integration of your electrolytes. The real conversion of CO2 actually happens in step 4, because you regenerate your electrolyte here. The net conversion of CO2 in the electrochemistry is actually 0. But maybe that's a bit too much. You can ask questions if you want to know that in more detail. Where do we put those things? Again, we put those on site. That's at Waternet and at HWC, so a water treatment facility in Amsterdam. And in Alkmaar, there is the energy center of HWC. And there we use the flue gas from beewood incineration. Both of them have carbon capture units, which then basically make sure we can put the CO2 into our units here. You can see a little mock-up of the unit on the top. Yeah. Why do we make those 3 things? I talked a bit already. The consumer goods, what is formic acid good for? Well, basically you can make toilet cleaner from it. It's good for descaling of limestone. Leather tanning also uses formic acid. We work with Nordic fish leather. They make leather from fish skins, a sustainable alternative just to cowhides, and you use more of the fish you're fishing, basically. So there's also a win-win there. As they are in Iceland, it might also be interesting for them to not ship the acid all the way to Iceland, but you can make it on site from the CO2 you capture there. That's the idea with that part. And then we have the deep eutectic solvents again, where you can recover metals such as copper or lead from different waste streams. So you can make your waste collection and separation recirculation process more efficient. And secondly, I want to talk about the polymers we're making. So you can't just make formic acid. You can also go to longer lasting things, such as polymers. And we do that in the hiccups process. Basically, again, we use biogenic CO2. On the bottom left, you can see that. Here we have a partner which also tries to capture and separate the CO2 with a new technology. That's Funditech and Aqualung. Syntef is also included here. And then we don't stop the conversion with the CO2 formate. We turn the formate into oxalate. Again, there's an acidification step. Everything is more integrated here. And in the end, we turn it into a polymer. We go to glycolic acid and turn that into a polymer. And well, basically, we want to, the reason we want to make new polymers is because polymers basically have a big impact on the planet, especially the polymers we have now. You might be aware of the high carbon footprint. It's made mainly from fossil fuels, and it impacts really all the, apart from the aerosol loading all too much in the air, it really goes into all the planetary boundaries and affects them negatively. So that's why we should make also not just CO2 based polymers, but also really better polymers, not the same polymers potentially. We want to make them more circular so you can reuse them, but also if they end up in nature, they should be better. So I'll skip this slide. It's maybe with time, it's a bit bad. It's a bit complex, but at the moment, I want to highlight that at the moment, 10% of all plastic waste is only recycled. So a lot of it really ends up somewhere else. 14% is incinerated and the rest goes to landfill. So we really want to go more circular, but we really have a problem because at the moment, there's really very little that is actually not ending up in landfill. So what we want to make is PLGA. It's a polylactic glycolic acid. And we want to do that because it's recyclable. You can do closed loop recycling, but it's also compostable. So you can home compost it. You don't need a fancy composter, industrial one. It's degradable in marine environments. It completely goes away. You don't have microplastics left. It has an excellent barrier property against oxygen and moisture. And it's CO2 based. So it's a quite nice polymer, not for every application. You make it basically from CO2 going to glycolic acid, and then the other part is lactic acid. You only need a little bit of that. And that is a bio-based polymer. But at the moment, you need to purify the glycolate. You remove all the water before the condensation step, and that at the moment makes it expensive. So that's why we have developed a new way of making the PLGA, and we're also developing a new source of glycolic acid in this process, adamantium. I think I have 3 minutes left and then no Q&A. So I go quickly over that. Basically, there's different ways of biodegradation. Ours is, of course, great at that. And there's different ways of doing that. This is something we study a lot at Avancium. Not in the Volta team, but in the CorpTech team we work with together. And basically because of the, not a slide, so the other way around. Basically what I wanted to show you here really is the degradability studies we've done. Basically what you can see here is the degradation, different incubation times. You can see polylactic acid that is already sort of one of the biopolymers you see a lot. And that degrades pretty slowly. So you have like 5 to 10% degradation over 8 weeks. Then we can look at cellulose, basically paper. We all know paper, if it's not treated, degrades relatively quickly. That's the black line. And what you can then see is like PLGA in that environment actually degrades even quicker than paper. So it's really highly biodegradable. And you can also see that on the right. So basically with the barrier properties you have with the PLGA, PLGA might be, for example, a really great way of coating paper. So you add barrier properties to paper for a certain time, and then you can put it into the same paper recycling streams. You don't put like some non-degradable plastic liner on your paper, but you put something that is compatible and degrades. So if it ends up in nature, it will degrade and not cause microplastic problems over the long term. Yeah, that's a bit the idea of what we do there. And maybe there's some times for some small questions. Of course, I want to thank all of our team. I'm not doing that by myself. I'm part of it. And yeah, I hope you enjoyed the talk.
Definitely. Yeah, I think we have some time for questions. Dušica, would you like to moderate this session? Or?
Yes, indeed. Then I would start with one that is addressing all the speakers. I think all of you touched on this topic in your presentations, but maybe you could answer Doris de Guzman's questions for all the panelists. From what I heard, converting CO2 into chemicals takes a lot of energy, whether you're using electrochemical or biotechnological processes. Hence, some petrochemical companies just use CCS instead of CCU. What is your opinion on the high energy usage? And maybe you could also introduce how you intend to tackle this challenge. Would you like to start, Francesca?
Okay. Well, that's the big question. It is an energy-intensive process, CCU. That's no doubt about that. As it is also very energy-intensive, the CCS. So it's difficult to make a direct comparison or a fair comparison, but what we can say is that energy intensity, it's a commonality of process of this kind at different levels. The solution, I mean, it's not a one solution. Of course, it has to be also seen in the in specific contexts. Like, for instance, where I'm based in Norway, we have quite some green energy that we could divert into this kind of activities. So it's quite of an advantage, but it might not be the case, and it is not the case elsewhere. So we can do some work on trying to optimize the energy, basically how we use the energy surplus, or when the energy is less expensive, and to see if we can couple our processes to those, let's say, period. But this is very complicated, and it might be negative for the process itself. I'm not sure that this is an answer. But in any case, I think it's very good to keep asking these kind of questions, because that's a little bit, the other side of the medal of the CCUS overall. Yeah.
Thank you. Would the other two speakers from the projects maybe like to elaborate on their experience?
Maybe if I can add something. For us, the difference between CCU and CCS, it's not both in both you use CO2, but when you use CCU, you are also producing something that could be produced from fossil fuels. So you are providing an alternative. So here it's two winnings. Huh? So you mitigate CO2 emissions and you produce something that in the past was produced by fossil fuels. So that's, for us, our bet is going to CCU in this case rather than CCS, which is also a possibility.
Eric, would you have something to add?
I think so. For sure, energy efficiency is a big topic. I think I said also this is the one thing we really try to use our electrons more efficiently. I think one other way of looking at it is that if we want to stop using fossil fuels, which we should and have to, and address the other problems like microplastics from existing polymers, for example, there's not really a good alternative to doing that. So if you use renewable energy and you have to work on efficiency, it is energy intensive. In the end, you're turning around the burning process, right? CO2 comes out when you burn something. You have to put that energy back in. But if you want to keep using and making plastics or other chemicals and don't want to cause a CO2 footprint, you have to do that. Whether CCS is, I think that needs a much bigger scale. If we look at the projections, it's chemicals is only one small part of it, and whether CCS after making chemicals is more efficient than making CCU in the beginning, that has to be seen. But I think also it should be clear that CCU is not a direct competition to CCS. You probably need to do both to get the CO2 levels down as much as we need to.
Thank you. And Pia, as you have looked into plenty of different CCU technologies and CCS solutions also, what is your prospect on the topic?
Yeah. So I agree with the previous speakers, and but I would like to highlight that if we have a look into the petrochemical industry as such, also everything coming from, for example, steam cracking, the whole steam cracking process, from the steam cracking itself to the downstream product, is also a very high energy intensive process. And the question here is, so where's the energy coming from, and how much do we have to pay for the energy? And this also is related to, I think, one of the first questions of the cost competitive of CCU. And if we put this all together, if we would like to to use CO2 as a feedstock, we need renewable energy, and we need cost competitive, cheap renewable energy. And the most energy we need and the most price we have there and the most cost we have there is in the CCU context, maybe when you need hydrogen to reduce the CO2 and to make it available. So we need cheap renewable energy to produce cheap green hydrogen to go into the CCU value chain for some of the process, not for all of the processes, but we also need the cheap renewable energy when it comes to electrochemistry, for example. And coming to the cost competitive, as Europe, we are also in the petrochemical industry currently not cost competitive, because all of the steam crackers are closing down because for example, ethylene here, you pay 3 times more than import the ethylene from the US. So this is also something you have to consider. And if we would like to have net zero chemical industry in Europe and worldwide, we have to tackle this and look at this from several different angles. So we need renewable energies, we need the sufficient supply of cheap green hydrogen for CCU, and we also need political incentives in this case. And of course, we need the technologies, but we have the technologies and we need to use CO2, because this is also the scenario that I showed you before. This is not only our scenario, but there are, I think, 16 other net zero chemical industry scenarios out there. And they all say, if we would like to have net zero chemical industry in 2050, we need CO2 as a feedstock, because we cannot transition from the fossil-based chemical industry to a renewable carbon industry without the use of CO2, because we can not only use biomass, because the land availability is not that high, and we also cannot tackle this with recycling, mechanical and chemical recycling alone. So yeah, this is more an overarching approach, but this is everything we have to consider in this regard.
Thank you for providing a perfect transition to the next question. So I think this gets us to cost competitiveness, which is the key question with all the solutions we develop. And Ronald would like to know, how cost competitive are the CCU conversion pathways you introduced versus fossil-based counterparts? I guess all of you looked into it. I heard some of you did a TEE and different assessments. So maybe you can tell us a little bit on the current state, and maybe also look at the scale-up scenario once you reach a higher TRL level. Would anyone like to start? Francesca?
I can start.
Perfect.
I can start. I think, for us, it's a bit in a way, if I can mainly comment maybe on the polymers. I think if you look at fossil-based polymers, it's quite difficult because of the huge volumes that are produced there. So you also have to include more than just the kilo price of your polymer. You have to include benefits in terms of performance, for example. And in that case, if you look at PLGA one-to-one, how it is done now to how we make it, we might actually beat that. But PLGA now is really, really expensive. You use it in many medical applications. You cannot easily compete with things like PET. So I think we have to look a bit further than just price per kilogram. And there is definitely still a way to go. But you have to probably beat fossil-based polymers also on performance, not only on price. So if you have better performance, you can use less of it, and then the price you need, for example, to make your product is equivalent or just a small amount more, because you need much less of your polymer. That is at least one way of looking at that.
Albert, as your project is concluding, what is your experience?
Our project, it was a very low TRL. So it's, as you know, it's very difficult to make predictions with lab scale. And what we realize, if we really want to scale up all the processes that we have done from CO2 to the production, for example, of succinic and itaconic acid, now it's very difficult to calculate because the efficiencies are going to get lost in this scale up. But something that we realize is that maybe we want to go step by step. So if we really can, for example, I mentioned it very shortly in the presentation. When we started the project, formic acid was just intermediate, but now, as Eric also pointed out, it has a lot of importance. And maybe if we could just start producing formic acid in a more efficient way, then we can go into the utilization of formic acid for microbiological process. So we don't need to scale up all the, let's say, all the Vivaldi pathway that we have developed in the lab, and we are going to go step by step. So if we take all the process, of course, now it's not competitive for the production, for example, of lactic acid, which is crazy because lactic acid is a commodity produced with a very low price. But we are trying to go maybe, say, piece by piece, try to optimize it. So now our first objective could be, for example, formic acid.
I would like to add something that I think is key when it comes to the actual implementation. I think that policies and support is really crucial, because as it is today, it would be really hard for any company to just have it developed and also make it profitable. This is not possible. So I think that we need to find the resources somewhere else, and I mean policies and all the different possibility for investments are really crucial to make. I mean, we cannot compare things with the fossil base. It's an industry that has repaid itself many times. So we need to make them more advantageous to use this CO2-based chemicals or materials. The profit has to come from something else, taxation, you name it. But I think that the policy push, it's really important. Just to conclude on this note.
Thank you for elaborating. So some of you have already mentioned that you conducted LCAs, and Atakan would like to know if you did so, which you confirmed, but also if any of the first results imply that CO2-derived chemicals are actually more sustainable in comparison to their fossil-based counterparts. Can anyone disclose any results already?
Yeah. I mean, we looked at PLGA. There's also a paper out on that recently. There is a lower impact. I think the one thing is there's across the board, there's a lower impact. It really, if you do it electrochemically, it really depends strongly on your electricity mix. So if you do that today and you plug your reactor into your power socket at home with all the fossil fuels being burned, chances are very high you're going to emit more CO2 than if you made this product in the conventional way, just because you have the inefficiencies of turning fossil fuels into electricity. But if you use more and more renewable energy, the carbon impact is much lower than fossil comparisons. That's what we found out in this case. But one thing, because we always talk about CCU, I think if you look at the lifetime, and that is for many products anyways, you cannot say that you store your CO2 a lot. So if we come quickly back to the CCS question in the beginning, if you want to store your CO2, you don't do that very long. If you, for example, make formic acid and use it as a toilet cleaner, or if you make a polymer that biodegrades, because then you emit CO2 again. So I'd be a bit careful to say it's really a solution to storing CO2 in the long term and not having it in the atmosphere, but it prevents putting more CO2 in the atmosphere. That's, I think, how you need to see it a bit.
Okay, so we are 15 minutes over time.
I would like to take one more question and then conclude. Is this fine?
Okay. Yes.
This one is looking to the future. To all speakers also, what are the potential collaboration opportunities for licensing and partnerships in developing countries? And to ensure transfer of the developed technologies. You all successfully implemented.
I think it's very important to consider energy mixes, energy sources, prices, and also suitability of the infrastructure. Yeah, I think that these are the key points for thinking about implementation pretty much anywhere else in Europe, US, China, and so on and so forth. Yeah, to summarize.
Would anyone else like to add something? Maybe Pia, you looked into the EU scenario, but maybe you could also give us a global outlook.
Well, not only in the future, also in the past and currently, there are a lot of transnational collaborations going on. So between South Africa, North Africa, and Europe, there are a lot of projects currently in the CCU vicinity. So when it comes to the low-cost production of green hydrogen. Yeah, this is just an example. So there are a lot of transnational projects currently going on. As far as I know, yeah, between Africa as one example, and I think maybe to reach out or to have a look at the European Commission site and all the funded projects, and maybe also get in touch with all the research institutes in Europe or also the US, if you would like to get in touch with them and yeah, build a collaboration for CCU implementation. Yeah.
Would any of the other speakers like to add something? Not yet. In this case, I would like to thank all the participants for joining us today, also to all the speakers for contributing your time and expertise. And in case you would like to visit further episodes, please subscribe to the newsletter. We'll keep you up to date. There's more coming up once we confirm the dates, and we will make all the slides and recording also available on the WaterProof website. Thank you so much, and good luck to all the EU-funded projects, and see you soon. Bye-bye.